Have you ever wondered what would happen if you looked up real astronomical data for, say, the Sun, and then tried to use this information to draw a line in the given direction for your location? And what if we did this for multiple observers simultaneously from various locations around the world? Would these lines converge to a single point in the middle of the Sun? How about the Moon or a planet? Well, these are the questions I'm hoping to answer in this project. To do this then, I'll first have to gather the relevant information I need from a website such as the US Naval Observatory. With this URL entered into my browser, I can get very precise information on many celestial bodies. The URL contains the time, the date, and the observer's latitude and longitude. Let's say my focus is on the Sun, then I'm wanting to use this information here. Specifically, the Sun's declination and Greenwich hour angle, the computed altitude angle, the azimuth angle or direction from north, and this last angle accounts for parallax, which we'll look into later. Using the Sun's declination and Greenwich hour angle, I can position this point on the sphere. This is the geographical position of the Sun, and it's the place on Earth where the Sun will be directly overhead or at zenith. We also have points A, B and C for our observers, the coordinates of which I've entered using this preset. Here you can see where I've entered the data for each observer and for the celestial body we're observing. If you'd like to try this yourself, then this is where you'd enter your own values. You'll notice I have distance information here too, and while I don't need it for triangulation, you'll see why it comes in handy in a bit. And here you can see all that information laid out in this table. Note that I've set the Earth's radius to 6371 kilometers, which corresponds to 1 unit in this model. After entering all the required data, I'm now in a position to draw in some rays that extend outward from each of the observers A, B and C, being careful to give each ray the correct tilt and direction. And we can confirm these rays are aimed correctly by getting GeoGebra to measure them. So in the case of point A, we can acquire the zenith angle like so, while the altitude angle is the complement. For the direction, we can get GeoGebra to measure the angle from north, and as you can see, it's a match for the value in the table. Now that we know these rays are correctly aimed, I can place a target disk a short distance above the surface of the Earth for each ray to hit. This disk has the same radius of Earth and is perpendicular to the GP ray, centered on point D, which is where that ray intersects it. This table shows how far each intersection point is from the center of the disk, and as expected, the points are thousands of kilometers off center, and that's fine for now. The big question is, do these rays still intersect this disk when we move it further out into space? So this is our Earth-sized target now. It's now over 152 million kilometers away and is placed at the distance the rays are expected to converge. And as you can see, the rays are still intersecting it in pretty much the same places as before, which is really quite remarkable. To put what we're seeing into perspective, as the Sun is 109 times wider than the Earth, then this is the equivalent of lining up 109 Earth-sized marbles, sitting side by side, spanning its entire diameter. These rays are all hitting the marble that is smack bang in the middle, the 55th marble. But what if I could get these rays to not just hit the middle marble, but get them to hit the actual centre of the middle marble as well? And this is where these parallax values come into play. So why do we need to correct for parallax? Well, even though each ray was constructed using a local coordinate system, their initial direction started out from the centre of the Earth. Moving each ray to the observer locations on the surface introduced a small angular difference in each, and that's what we need to correct for. This slider here controls how much of that correction is applied, 0 being none at all and 1 means fully corrected. Shall we give it a slide to see what happens? So what did we notice? What was thousands of kilometers off is now less than 20. And before we look at the reasons as to why they're not exactly centre, let's take a very quick look at 2 more examples. This one is for the Moon, and the rays here all converge to about 5 kilometers from the centre. And this one is for planet Mars, and as we can see, these rays are all about 10 kilometers off. So this is all very impressive, but if you're anything like me, then you're probably wondering why the rays didn't all hit dead centre. Well, the main reason is my observer positions are on a sphere, not an ellipsoid, which is what this observer data is based on. And while the difference in positions is tiny, by applying the data to a sphere Earth, the rays were never going to converge exactly to a single point out in space. So let's return to the first example for the Sun, but this time I'll make the smallest of adjustments to these values so that they work properly for this model. Are you ready? Done. Let's do that again. These are the original values, and this slightly tweaked to work for a sphere. No real difference in the direction of those rays, was there? Shall we see what happens when we apply the parallax correction? So using the correct model for the data is important if we're wanting precision, but it seems that a basic spherical model, while not perfect, is entirely sufficient for triangulation in many cases. And what if I created a proper ellipsoidal model instead? Well, that sounds like a project for another time, but for now at least, the initial questions have been answered and the shape of the Earth confirmed. So I think I'll leave this one here. There'll be a link in the description for this project if you're wanting to check out the geometry. And if you like this one, then maybe you can hit the share button and give it a big thumbs up. So yeah, thanks very much for watching, and I'll catch you later.